Alright, today we are just going to look at some exponential growth applications. Since I'm doing this from a video, we are only going to do some pretty straightforward growth problems today. We will look at the decay and the more complicated situations later. Technically, all of this stuff is really from Math 1, but I know it's been a long time, so you have probably forgotten some of it. Before we get started with actually doing the growth problems, I want to just quickly review how to change a percent to a decimal and a decimal to percent. So here we're asked to convert each percent to a decimal. To convert to a decimal, you need to divide by 100. Whenever you do that, it is just going to take wherever the decimal point is at and move it 2 places to the left. So in this case, 15 doesn't have a decimal, so it's at the end of the number, and you would just move it 2 places to the left. And so that would be 0.15 is what we would get for the first one. For number 2, the decimal is at the end of the number, so we move that decimal 2 places there, and it would end up right here, so we get 0.20. This 0 right here is at the end is unnecessary, so you might also see it written like this. Both of those are equivalent. For 400%, the decimal is back here at the end. We're going to move that decimal 2 places there, and when we do that, we get 4.00, but again, the zeros here on this one are not necessary, so a lot of times you're just going to see this as 4. Sometimes that confuses students because it doesn't look like it's a decimal anymore, but the decimal for 400% is 4. And if we do this last one, we need to move this decimal 2 places to the left. When we do that for this problem, we've got a blank space where we don't have anything. If you have any of these, you need to fill them in with a 0. So what we would get here is 0.013 for that. So we're going to need to change percents to decimals for this. Let's also look at changing decimals to percents. You're not going to need it so much today, but in some of the other stuff we're going to do, you're going to have this. You're just going backwards, so you're going to move that decimal 2 places to the right, and it will change it to a percent. So this would be 17% here. Make sure with percents that you put the percent sign to show it's a percent. For number 6, we would move that decimal 2 places. Now, much like the last problem we did on the other slide, I've got a blank space. There's nothing here, so I need to fill that in with a 0. So I would get 130%. Okay. For 7, I would move that decimal 2 places like this, and it would end up here. The zeros in the front are not necessary. This is just going to be 5%. And for the last one, I'm going to move that decimal 2 places, and that is going to give me 0.12%. This confuses students some here, where I still have a decimal in my percent, but that is possible. It's going to happen sometimes. Alright, let's look at our exponential growth/decay formula. Today we are only going to do growth problems, but the same formula applies for growth and decay. So the exponential formula that we're going to use is y equals a times b to the x power. In this formula, a is your starting amount, sometimes called the initial amount. It's how much you begin with for the problem. B is either your growth or decay factor. And then X is always going to be some sort of time. It could be in minutes, it could be in hours, it could be in days. We're going to see years a lot. In fact, we may have only put years on the problems that we're going to do today. Sometimes it's not a specific amount of time, but maybe like the number of rounds of a tournament or something like that. But it's always representing some sort of time in the situations that you're going to see here. Now, this growth or decay factor that we have for B, we have to figure out what that value is going to be. For our growth factor, whenever we have growth, to find that B, we're going to do 1 plus the rate as a decimal. Okay, and if we have decay, which we're not going to see until tomorrow, we would do 1 minus the rate as a decimal. Okay, so today we're going to be really concerned with that growth factor that we're going to use there. All right, let's look at some problems. All right, for number 1, the original value of an investment is $1,800. If the value has increased 7% each year, write an exponential function to model the situation, then find the value of the investment after 15 years. So for this problem, our equation is going to be of the form y equals a times b to the x. A is our starting amount. The original value of this investment is $1,800, so there is our A. We're going to have y equals $1,800. And then the value has increased by 7% each year. That 7% is what we're going to use to find our growth factor in this. So for that B value, to find it, we're going to do 1 plus our rate as a decimal. So the first thing that I need to do for this is I need to take 7% and I need to change it to a decimal. So I'm going to take this decimal, I'm going to move it 2 places to the left. So I end up here. I've got to fill in that open hole with a 0. So 0.07 is my rate as a decimal. So the B value here is going to be 1 plus 0.07. That will give me 1.07. This is a lot like what we were doing with sales tax. We have 100%, we add 7%, we change it to a decimal, it's 1.07. So that number goes here. And if we're writing the equation, I'm just going to put an X right here. In this case, that X is going to be my number of years, and the Y is going to be the value of the investment here. I know it's going to be years because this increase is per year for that. So if I want to know what the value of this is after 15 years, all I'm going to have to do is plug in 15 for my years right here. So I'm going to have 1,800 times 1.07 to the 15th power. And you can use your calculator or Desmos, whichever one you prefer. Let me pull up Desmos here. Let's see. Really don't need much here. Let's get rid of this stuff. We're going to do 1,800 times 1.07 to the 15th power. You don't have to do y equals or anything there. It is going to give us 4966.26. Normally we round to 3 decimal places, but this is money, so it makes sense to round to 2 decimal places here. So after 15 years, if you could get this rate, which is a very good rate, you would have almost $5,000 here in your account. Okay. Another place where this can apply is in the appreciation of items that you might own. Houses, for example, usually gain a lot of value as long as you don't destroy them and keep them up. So here we've got Maya paid $1,800 $160,000 for her house in 2011. Since then, the value of the house has increased at a rate of 2.7% per year. If this continues, how much will the house be worth in 2025? So when we're writing our equation here, it's going to be y equals our A value is our starting value. So this is our A value. It's how much we started with. So we're going to have 160,000 goes here. To find our B value, we're going to do 1 plus our rate as a decimal. So we got 2.7%. We need to change it to a decimal, so we're going to move that decimal 2 places to the left. We're going to fill in the open hole with a 0. So we got 0.027. That will give us 1.027 for our B value. So that is going to go right here. You can use the dot or you can use parentheses. I'm going to use parentheses this time so you just see it looking a little bit different. Either one of those mean multiplication. And then we'll raise it to the x power. In this case, we are still growing per year here. So our time up here is years. And then y would be the value of the house. There. So I want to know how much the house would be worth in 2025. In this particular case, I don't want to plug in 2025 because that would be 2025 years from 2011 because that's our starting value. Instead, I need to figure out the number of years that have gone by. So I'm going to do 2025 minus 2011, and that's going to give me 14 years here. So if I want to figure out the value of the house after 14 years, I'm going to do 160,000 times 1.027 to the 14th power. And I'm just going to go over here to Desmos really quickly and type that in. 160,000 times 1.027 to the 14th power. And I am getting 232,330.48. So I've got $232,330.48 as our house value there, which is probably actually even going up a little bit more than that in a lot of places anyway. So let's continue on to our next examples. Another place you're going to see this used a lot is population. So in example 3, we've got the population of Algebra Acres was 3,150 in the year 2014. The population is growing at a rate of not 7% per year, but 0.7% per year. If the growth continues at this rate, what will the population of Algebra Acres be in the year 2030? So in this case, we are going to do y equals, we need our starting value. That is going to be 3,150 here. And our growth rate here, we got to use for our B value. Remember, it's going to be 1 plus our rate as a decimal. So this is a little confusing because it's already a decimal, but this is the percent. So I still have to move my decimal 2 places over here. So when I do that, let me do that where I've got a little bit more room. I've got 0.7%. So I'm going to move that decimal 2 places, and the blank spots, I've got to fill those in with zeros. So this is going to be 0.007, meaning that our B value is going to be 1.007 here. So that number goes here, and we raise it to the x power. In this case, that x right there is where we put years. And the y in this time is not our value, but our population. So if I want to know the population in 2030. This is similar to the last problem. 2030, I have to subtract 2014, which was the first year that we had data here for algebra acres, and that is going to give me 16. So I want to do 3,150 times 1.007 to the 16th power. And we're just going to skip over here to Desmos and type that in. 3,150 times 1.007 to the 16th power. And we are going to get 3,521.941. In this particular case, we're talking about a number of people. So I would actually go ahead and round to the nearest whole number on this one. So that would be 3,522 people would be our population for that problem. Okay. Now let's look at our last problem. So we'll continue our theme of seeing how Angel's doing on his Kool-Aid sales. So let's say Angel makes $400 selling Kool-Aid at school. He decides to put this money in a certificate of deposit, a CD, that earns 5.15% per year, interest per year. If he leaves the money there for 5 years without making any deposits or withdrawals, how much money will he have in the account at the end of the 5 years? So a certificate of deposit is like a savings account sort of that you cannot take the money in and out of. You just have to let the money stay there for whatever term we have here. So whenever we write our equation for this, he starts off with $400. And he is earning 5.15%. So we need to take 5.15%. We need to change it to a decimal by moving that decimal 2 places. And so for our B value, we are going to have 1 plus 0.0515. That is just going to give us 1.0515. So that is what we're going to use as our B value. It doesn't matter whether you use parentheses or the multiplication sign. Either one will work. Like that, and it will be raised to the x power. So this is still interest per year, so this is still years. There are other increments of time that you can use, but all of my examples here lend themselves to being years. And then this right here would be the value of the CD, or the certificate of deposit. So that account, what it's worth. And so we want to know after 5 years how much money he's going to have. So we would plug in 5 for our x. So we would have 400 times 1.0515 to the 5th power. And if we go over here, we'll have 400 times 1.0515 to the 5th power. And we can see that he would have 514.17. So $514.17. So in that amount of time there, he would earn about $114 just for letting his money sit there in the bank. So these are only looking at growth right now. We're going to look at some more types of problems that you might see for this that involve exponential decay tomorrow, but today it's just a little practice with growth.